This conference will now be recorded.
So, good evening. Today we'll be discussing moment of inertia, radius of gyration, perpendicular axis theorem, and parallel axis theorem related to moment of inertia. So, mainly today's discussion will be on moment of inertia, and this is actually belonging to where we were discussing system of particles and rotational motion. So, before I go to the formal definition, let me tell you what is, like, philosophically, what is moment of inertia. See, we have so far learnt in the laws of motion. From the first law, Newton's first law, what we have learnt. So we have learnt that if the external force applied on any object is zero, then what happens? So this is for linear motion, not for rotational motion. So if in case of linear motion, if external force is not applied or external force is zero on any object, then that object will either be at rest if it was earlier at rest, so it will be continuing to be in rest, or if some object is moving with uniform velocity, that will continue to move with uniform velocity. So that is what was actually that property by which the object could maintain or sustains its state of rest or state of uniform motion was called inertia. So first law, Newton's first law of motion actually deals with the inertia of any object, and the measure of inertia was said to be the mass of the object. If the mass of the object is more, suppose this is m1 and some object is this m2. If this m1 is greater than m2, then m1 has greater mass than m2. That means it is having greater inertia than this one. Okay, m2. So what do I try to say here is, we have seen that in case of, see, okay, let me just finish it. If the inertia is more, if inertia is more, so more effort is needed, more effort or force may be needed to change the state of motion, change the state of any object. Okay, so this is what we have learned in Newton's first law of motion. So because of this inertia, what it does, actually it opposes the force. Okay, it opposes the force to change its state of motion. And we have seen that, see, linear momentum p has rotational analog, or P, linear momentum is the rotational analog of angular momentum. Okay, so we have obtained this kind of analog quantities, like see, force is analogous to torque here. Okay, so we can see there are direct correspondence or direct analogous quantities, like momentum. Linear momentum is analogous to angular momentum. Force is analogous to torque, etc. Then why can't we have, see, if we have linear inertia or inertia of linear motion, inertia of linear motion, linear in the sense, linear I would not say, I will say translational motion. Okay, so I'd say inertia, if there is inertia in translational motion, translation, then there must be, so inertia must be there in case of rotation also, right? In case of rotation also there must be inertia. And see, in case of translational motion, the mass is actually measure of inertia. And you know what it is in this case, in rotation? So it is the moment of inertia which is denoted by I, which is analogous to the mass, or the translation inertia, or inertia in the translational motion is mass, which is analogous to moment of inertia in case of rotational motion. So in case of rotational motion, moment of inertia, which is denoted by I, we'll see what is the mathematical form of it. So this is the analogous quantity. We'll discuss in detail what is the physical significance again, and then let me tell you the definition then. So look, see, we have analogous quantity, linear momentum, angular momentum, then you have force, torque, then we have got another analogous quantity. M is like analogous to I. Okay, I is the rotational analog of or in like we can say M is the rotational analog of inertia. Okay, or yeah, let us say what is aim in translational motion. The same, like same role is actually, same role is done by moment of inertia in case of rotational motion. Okay, that's what we can say. So these two are also analogous quantity, rotational inertia, which is moment of inertia, and this is mass in case of translational motion. So this is the measure of inertia in translational motion, mass. Okay, let me give you the definition. So moment of inertia of a rigid body about a fixed axis is defined as the sum of the product of masses and constituent particles, and sum of the masses of constituent particles and the square of the distance between their respective distances. So this is actually the definition of I, rotational inertia. Okay, in terms of mathematical form, let me tell you what is this definition saying. Suppose I have an arbitrary object which is constituted by many such particles like m1 having mass m1, which is, see, this object is suppose moving with respect to this particular axis. Okay, which is out of this rigid body, like outside the rigid body. Anyway, suppose this is rotating with some angular velocity I. Okay, angular velocity I, this is rotating like this with respect to this axis. Okay, and this object is constituted by many such particles like m1, which is actually situated r1 distance away from the rotation axis, and here is m2, which is at r2 distance away, and I can go like that. See, this is m3, it is at r3, and maybe we have some n particle here, so it has mass mn, and it is rn distance away. Okay, you can have such particles like which is constituting this rigid body. So what is the condition? Condition is that the distance between particles will be always remaining fixed. So that is the definition of rigid body. So a rigid body can be considered considered as constituted by many such particles. Okay, and this rigid body is rotating about this axis. So according to the definition of moment of inertia, this is actually the sum of the masses, sorry, sum of the product of the masses, sum of the product of the masses and of the constituent particle and the square of the distance. That means, see, if I take the mass 1 m1, so mass and square of the distance between respective distance from the axis. So square of the distance between their respective distances from the axis of rotation. So m1 has distance r1, so I can write r1 square. So see, this is the mass and the square of the, like, this is the product of mass and the square of the distance from the rotation axis. If I take m2, then you have m2 into r2 square. So product of the mass and the square of the distance of the constituent particle from the axis of rotation. Okay, so such, see, if I write m3 like this, I can go up to the total number of particle like this. Okay, so this is the definition of moment of inertia for this whole object. See, whole object, then I can write in terms of summation mi ri square. Okay, so this is the definition of the moment of inertia. Okay, so I can go from 1 to n here. So look, this is called also, this moment of inertia also called moment of inertia, moment, moment of inertia. Let me write it again. Moment of inertia is also called as rotational inertia. Rotational inertia. We can give another alternative definition of moment of inertia, that moment of inertia of any object about the given rotation axis is defined as the quantity, by virtue of which it opposes the torque which changes the motion of the object. Okay, let us first do one thing. Let us get the SI unit of this moment of inertia. So we have seen, I'll write in short the definition of this. Sorry, this, yes, mathematical expression for the moment of inertia. I'll keep this part alone and I'll remove this also. So we are going to find out what is the SI unit of this moment of inertia. SI unit of moment of inertia. So SI unit of moment of inertia. Okay, I'm writing MO. Actually, moment of inertia in short can be written as MOI. MO, moment of inertia. MOI. Okay, so see here, you look, this is the mass and this is the distance square. So I can write SI unit is kg into meter square. Okay, kg meter square. So this will be the SI unit of moment of inertia. So kg meter square. Okay. Now see what is the physical significance and what are the factors. Let me first tell you what is the physical significance of this moment of inertia. I had already briefly told you, but still I'll discuss what is physical significance. See, in case of linear motion, mass actually is the measure of inertia, and it resists the change of its motion. Okay, change of its motion. Okay, change of its motion. We have seen that. So, in case of rotational motion, the moment of inertia of a body about any axis of rotation resists the change in rotational motion. So if we want to have a change in the rotational motion, what we apply is torque. So rotational moment of inertia, that is, sorry, rotational inertia or moment of inertia actually resists the change in the rotational motion, and that's why it acts against the torque. So if some object has greater moment of inertia, what does that mean? You need greater torque to change the state of motion, rotational motion of that particular object. Okay, if you have less torque, then it is easy to change the state of rotational motion of that particular object. Okay, that is the physical significance. So mass in linear motion, and here the moment of inertia, which is denoted by I, and which is summation over mi ri square. So these two, m and m in the linear motion and this in the rotational motion, acts in the same way. So that's why I can be given, like, I can be told as rotational inertia also. Okay, so this is about moment of inertia. Now let me tell you, if suppose your rigid body is not constituted by such discrete particles, if you have a continuous mass distribution, then how to write the moment of inertia in that case? Let me tell you that. Suppose you have a continuous object. Continuous object, I'll tell you what it is. We have also discussed during the discussion of center of mass. See, continuous object means your particles. See, your particles are not that far. If the distance between interparticle distance between, like, distance between the two particles are very, very less, then see you will get, like, see, very closely spaced particles. So it will be it will be very difficult to find out one particle and their distance, corresponding distance, right? So in that case, you think this as a continuous object. Suppose you take anything. Suppose you take a bar or beam of rod, okay, iron rod, or you take a thin sheet of some metal. So you cannot find out one particle, like one particle of mass m, etc. So what you have to do, you have to consider an area in case of planar portion. Okay, suppose it is a plate of some metal. So you have to take an area, and in that case we defined mass part, like mass density. We had defined mass density, and we were taking, in case of this kind of continuous mass, so we are continuous mass distribution. So what we had taken, elemental mass. We have taken elemental mass or mass element. Element means tiny mass, but there may be many particles within that. So if you have a continuous object, then what you should do, you should take a mass element of mass, like this. Okay, if it is not a planar object, if it is 3D object, you should take volume element. So this is a small volume element. Okay, small volume element, small volume element. So in this case, you have to define rho. Rho is the mass density, that means total mass, by the volume, so you'll get rho. And from here, if you know the volume of this particular small, so suppose this is having a small volume element delta v, so dm will be actually rho into del v. Okay, so this is how, when you want to find out moment of inertia for this whole object, what you have to do, you have to integrate it. So we know moment of inertia is actually sum over mi ri square. So instead of taking, say, this summation, in this case continuous object, it will be converted into integration. So what I'll write, instead of writing m, I'll write delta m. And see, this r is fine, so I have taken volume element or this mass element at r distance from the axis of rotation, so we can write this r square. Okay, so now see, in this dm there will be rho into dv, so dm will be rho into dv, and dv contains this r factor. Okay, in case of in case of spherical object, you have to take volume element, so you will get, see, you will get 2 pi r square, sorry, 4 pi r square dr. Okay, 4 pi r square and dr, r square dr, like that. In case of two dimensional object, maybe you will get 2 pi r, like thick disk etc. 2 pi r dr, you have to take the, this is length, this is another length, so this is actually area element, so you have to multiply sigma into this for getting delta m. Okay, so this is how, so what I'll write in this case, the moment of inertia will be integration r square dm. And in this you have to write according to the structure or the net, the shape and size of the object, you have to write this dm either rho dv. Okay, or dm can be written as sigma d a. Okay, or maybe this can be written as lambda into dl also. Okay, lambda, this is the linear mass. Okay, so like that you can replace this dm with this, and dm, this will be, see, three dimensional. In, you can just think of a cube here, so you have to write the, like, volume here, you have to write the elemental area here, elemental length. Okay, so when we take specific example, after finishing the course, we'll take physical, some examples, then I'll tell you or discuss in detail. Okay, and then you have to take proper limit also, integration limit. That's how we can find out moment of inertia for a continuous object. Now what we do, let us, okay, so physical significance I have already told. Now let us see. Okay, so physical significance means you have to tell, see, mass is analogous to, like, rotational analog of this. Okay, so mass is inertia in case of linear motion, and this is actually rotational motion, rotational inertia, rotational inertia. So this is the physical significance. Okay, now we'll see on which factors moment of inertia depends. So we will write the definition here so that we can at least get some idea. Mi ri square. So look, naturally from here we can write, so first factor we can write mass of the body. Okay, second factor maybe can be written as the distance or shape and size and shape. So depending on this we can write whether it is summation or it is integration. Then maybe third point we can write the distribution, mass distribution, as I said. So shape and size will give you the distance, this r factor. And see, the mass distribution, nature of the mass distribution, this will distribution. So this will tell you whether you have to take, like, you have to take unit area. So you have to take dv or da or dl. That is what I had discussed already. And then fourth factor is the position and orientation. It depends, like position of the mass and orientation, position and orientation, orientation, orientation about the about the axis of rotation, axis of rotation. Okay, so these are few factors on which moment of inertia depends. So what is that? So one is mass, then shape and size of the object, then mass distribution of the object. Depending on that, you can find out like whether it will be integration or it will be just summation, or if integration, then whether it is volume integration or like area integration or line integration, what it is. And then position and orientation of the about like position and orientation about the axis of the rotation. Okay, so these are few factors. Now what we'll see, application of, okay, I'll just remove this part. So application of this moment of inertia. Okay, so just a minute, there is some problem in the typing. I'll just remove this. Okay, so factors we have learned already. Now application of moment of inertia. See, we have seen in case of like cartwheel, or maybe in case of bicycle also, the whole mass actually, the more mass is actually put in the rim, right? Put in the rim. Why is it so? So this is the mass, and this is empty space actually. This is empty space. We have seen these are the spokes, and this actually empty space. Why is it so? See, by doing this actually, you know what happens. I is equal to, suppose I am taking m r square. Summation over m is, so this is m r square, right? So this, see, if we put more mass, then moment of inertia increases. Okay, or if we somehow increase this distance also, mass from the axis of rotation, then also moment of inertia increases. So in case of cartwheel or bicycle wheel, see, the more mass is put on the rim because you need to increase the moment of inertia. So what happens after paddling for some time, if you just stop paddling, so what happens, the bicycle, like you usually move, right? After cycling, after paddling some time, you can stop the paddling, but still the cycle moves. Why is it so? Because of this moment of inertia, even if you have stopped the motion, like paddling, but the motion of this object is not stopped, because moment of inertia, if the moment of inertia is more, then it is not that easy to stop or resist the motion, rotational motion of the object. So it is not easily stopped. Okay, so this is the advantage, or this is kind of application we do in many places. Similar applications are there, flywheel, in various machines, etc. Okay, so this is one of many applications. Now see, we'll learn another interesting term, what is called a radius of gyration. What is radius of gyration? Let me first define what it is. See, radius of gyration of a body about its axis of rotation may be defined as distance from the axis of rotation at which, if the whole mass of the body were concentrated, its moment of inertia about the given axis would be the same as with the actual mass distribution. What does this mean? What does this mean is actually, see, suppose, okay, so suppose I have such object. Okay, this is an object which is constituted by m1, m2, m3, etc. So they have their different distances from their axis of rotation. So if I want to find out moment of inertia, then what we have to do? We have to write m1 r1 square plus m2 r2 square. Like that, you have to find out the total moment of inertia. So this is one way to find out moment of inertia. Okay, for discrete, like for a rigid body with discrete mass constituted by discrete mass. Okay, so like this one. Okay, but radius, what is radius of gyration? Actually, radius of gyration is defined as the distance from the axis of rotation. Suppose this is the axis of rotation. Take a point, if I take a point from the axis of rotation, and if I think the whole mass, suppose this is k, distance k, and whole mass is concentrated at this point. Suppose the summation of m I, actually capital M. If the whole mass is concentrated over here, then see what we can write. Moment of inertia will be the same as you get here. Okay, so mk square, this will be the moment of inertia of the object, and this is equal to this. So this is the definition. So moment of inertia, moment gyration, radius of gyration is the radial distance. Okay, radius radius of gyration is the radial distance of a particular point on the object. Okay, from the axis of rotation, given axis of rotation, where if the whole mass of the object is concentrated, whole mass m is concentrated, then the moment of inertia about that particular, this about that moment of inertia about that axis will be same as the moment of inertia with the actual mass distribution. Okay, so the moment of inertia with actual mass distribution is this one, and see k is the radial distance from the rotation, axis of rotation, to that particular point where the whole mass is concentrated. If we just think this, then the moment of inertia for that point, moment of inertia, see about this, will be written as, about the same axis will be written as mk square, and this is according to the definition of radius of gyration. This will be equal to the moment of inertia if we calculate with the real mass distribution, which is, see, if suppose this is an object which is constituted by such discrete point masses m1, m2, m3, like that. So moment of inertia, you can find out individual moment of inertia of, like, all the particles what you have. Okay, individual moment of inertia of the particles, and then sum it up, and then you get the total moment of inertia. Okay, this is actually the moment of inertia, actual moment of inertia, or moment of inertia with actual mass distribution. And this is actually going to be the same if you get a point, a geometrical point. Actually, this is not a real point, this is a geometrical point or imaginary point. If you consider from the axis of rotation, suppose it is at r distance away, k distance away, then mk square will be the moment of inertia of this object, which is equal to this. Okay, let me derive the respective numerical form of this. Okay, let me write the moment of inertia of this object according to our, so m1 r1 square plus m2 r2 square, m3 r3 square, like that. If I go up to mn rn square, now look what I'll do. Suppose there are n particles, so what I can do is, let me do one thing. let me take this all point masses as same for the time being. Let me take all these point masses are same, that is all m1, m2, m3 dot mn. So let they be equal in mass so that they are taken as m. If I take them as m, then I can write this, rewrite this. Okay, r1 square plus this is r2 square plus dot rn square. So what I have supposed, I have supposed that all the point masses are having the same mass, m. Okay, so what we can do is, see, I can write m into n, and I can write dot r n square divided by n. So this n, so will cancel out. So the equation will not have any change in the dimension or magnitude. Okay, so this m into n, so n particles are there of m mass, so I can write the total mass of that is this. Okay, so look here, this part is remaining the same. I'm not writing because of the space crisis. So what I'll do, I'll just write here. Okay, so now what we'll do, now let us take k is another distance. So as I was telling you, suppose k is the distance. So this is k, is the distance where the whole mass is concentrated. So see, look here, we have got moment of inertia by actual mass distribution. What we have got, I'll write finally. So we have got, this is m into this part. This is this. Okay. Now look, what I can write from this is this. This is another moment of inertia. Okay. This is actually geometrical moment of inertia, I can say. Geometrical, this is just geometrical point. So this will be the moment of inertia, and see, these are actually equal. So I can put this value here. What I can write is m, and this is r1 square plus r2 square, then dot it goes up to rn square divided by n. Okay, now if I want to calculate what is this radial distance, see, m goes off from both sides, and see, this can be written as r1 square plus r2 square plus dot rn square divided by n. So what does this mean? This is the root mean square of the distances. That's all. So see, if we want to write the definition from this particular form of the radius of gyration. So what is radius of gyration? It is actually, so hence we can write radius of gyration, gyration of a body about a given axis is defined from this particular expression. It can be defined as the root mean square, root mean square of the distances from the given axis. Okay, as the root mean square distances of its particles. Okay, root mean square. So root mean square distances of the particles from the given axis. Okay, from the given axis. So this is from here. It follows from here. So K is the radius of gyration, which is the root mean square of the distances of the particles from the given axis. So what is the physical significance of this? Actually, it is a geometrical position. So actually, this is a geometrical concept of moment of inertia. Okay, and it depends on position and direction of the axis, position and direction of the axis of rotation with respect to the distribution of mass or the body, and obviously it depends on the distribution of mass about the axis. So there are two factors. One is the orientation or direction of the position and orientation of the axis with respect to the body, and the mass distribution. It depends on the mass distribution of the object with respect to the axis of rotation. Okay, so this is actually a geometrical concept of moment of inertia. So radius of gyration is a geometrical concept. Now what we'll do, we have got another 10 minutes. We'll just uh, maybe I'll take 5 minutes extra, but I'll discuss perpendicular axis theorem of, this is actually, I'll write related to moment of inertia, related to moment of inertia, moment of inertia, moment of inertia. So see, there are two rules or theorems. One is perpendicular axis theorem, another one is parallel axis theorem. These are the theorems which will help you to find out moment of inertia of various objects and in various orientations of the axis with respect to the mass distribution. Okay, let me tell you what is perpendicular axis theorem. So according to perpendicular axis theorem, so what it states that, so according to perpendicular axis theorem, I'm writing like this: perpendicular axis theorem. This means perpendicular axis theorem. Okay, or maybe sometime rotation like this also can be given. Perpendicular axis theorem. The moment of inertia. Suppose you have a planar object which is called plane lamina. Plane lamina. I'll draw somewhere. Plane lamina. Like you can take a disc also. Lamina means you have any arbitrary shape planar objects. Okay, planar object. So planar object means actually plane can be defined by two axes, right? See xy plane. You should have two axes. Okay. So there will be two axes on its plane, right? So planar objects, and see, and if you just think there is a perpendicular axis like axis perpendicular to that. Okay, I'm taking it. Okay, maybe I'll just do one thing. I'll take the axis. Okay, so I hope you have understood what I'm trying to say. You just take plane sheet of sheet of any metal like disc or any arbitrary shape, some plane object. So you can define mass distribution at any place by two axes on that. Okay, so look, here is plane lamina, this one, planar lamina, this one. Okay, so I'm just taking, there are two axes on the plane, oh sorry, in the plane, two axes in the plane, that is x-axis and y-axis, and another axis I am drawing perpendicular to the plane perpendicular to, similar to this. Okay, this. So you just take a disk, you have two axes, and perpendicular axis is z axis. Okay, this is the thing. So according to perpendicular axis theorem, the moment of inertia, okay, I'll write in short so that I can finish it in time. So the moment of inertia of any plane lamina, any plane lamina or any planar object about an axis, about an axis perpendicular to its plane, its plane is given by the sum of the moment of inertia, okay, MOI, moment of inertia about the axis in its plane, in its plane. I'll write what, like, in terms of mathematical numerical form so that you understand. So according to perpendicular axis theorem, the moment of inertia of any plane lamina about an axis perpendicular to its plane is given by the sum of the moment of inertia about the axis means two axes, okay, about the axis in its plane, in its plane. Okay, let me tell you. So what are the axes in this in the plane of this lamina, particular lamina? So axis is x axis and y axis. So if I say the moment of inertia about x axis is ix, okay, and moment of inertia about y axis is given by iy, okay, and let us say the moment of inertia about z axis, which is perpendicular to this, the plane of this lamina, is iz, okay. So according to this theorem, moment of inertia iz will be given by ix plus iy, okay, ix plus iy. So this is the theorem. Now we have to prove this. We'll prove it. Let us first learn once again what is this theorem. According to this perpendicular axis theorem, moment of inertia of any plane object you can find out, okay. So moment of inertia of any plane object about an axis which is perpendicular to the plane, perpendicular to the plane of the lamina, that is z axis, which is perpendicular to the planar lamina, plane lamina here, okay, or planar body. So this is iz. So moment of inertia, if this is iz according to this definition, so what it is? So moment of inertia about an axis which is perpendicular to the plane of the lamina is given by the sum of the moment of inertia of the object about its axis in the plane. So moment of inertia about x-axis plus moment of inertia about y-axis. So this is the statement of the theorem. Now let us prove this. So to prove it, let us see, let us think that this particular lamina is constituted by many tiny particles, and let us consider a such particle small m, okay, small m, okay, small m at this particular position p, which has coordinates x and y. So you know coordinates in the x and y plane. If I say this is x and y, this particular position p is xy, so this means it is having perpendicular distance y from x-axis and perpendicular distance from y-axis as x. Okay, right? So this is what it is. So I can write this distance. See, this is actually the distance from y. So it is x. Distance from y is, so if I sometimes suppose this is the rotation axis, so this mass, okay, so this mass is actually x distance away from y-axis. If I suppose x-axis as rotation axis sometime, then this particular object is at y distance away. Okay, so I can write the moment of inertia right here from this. So suppose I take that y-axis as the rotation axis. Okay, let me first write x-axis as a rotation axis. So if I take x-axis as rotation axis, then what is the moment of inertia of that particular point mass about x-axis is this. See, x-axis is given by m into x x square here. Sorry, not x square. So from x-axis, what is the distance of this particle? This is y. So this will be mass, product of mass into square of the distance from the axis of rotation. So this is the mass and product with the square of the distance. So this is the distance of y. So that's why I'm writing like this. So when the axis of rotation is y, then what is the moment of inertia about y-axis? See, I have to write the mass of that particle, fine, and the distance of that particle from the axis of rotation is x. So this is x square. Okay. Now look, according to, see, like what is the moment of inertia about this z-axis? Moment of inertia of this particular object. See this distance, if I suppose r. So what is this? What is this r? R can be written as, see, if you remember, x square plus y square, right? R can be written as x square plus y square, right? So I can write this moment of inertia about this particular point object about z-axis is like m r square, and this gives you m into this x square plus y square. Okay. Now see, if I want to calculate the moment of inertia of this whole planar object about x-axis, then you just take the summation of this. Okay, and about y-axis just take the summation, and moment of inertia the of the whole object about z-axis you take the summation. Then see, according to our perpendicular axis theorem, so you have to find out that iz is equal to ix plus iy. This you have to prove. So see, look here, what we get here is, see, summation. See, this will be summation x square plus summation m y square. Okay, summation m x square, summation over m y square, and you take the limit of the summation n to a, like 1 to n maybe. So in this case also 1 to n. See here also summation when we take, you can write 1 to n. So similar here. So look, this particular part is ix and this particular part is iy. So so see, we could prove this perpendicular axis theorem. So this is how you can prove the perpendicular axis theorem. We'll take up examples tomorrow. Sorry, in the next class, maybe Thursday, of this perpendicular axis theorem and parallel axis theorem. Let me just finish the parallel axis theorem. Okay, then we'll take up the examples on the next day, like how to use this perpendicular axis theorem, how to apply the parallel axis theorem. We'll discuss on the next class. So, so parallel axis theorem. Suppose you have a planar lamina like this, or any object in that sense. So the moment of inertia of a body, I'll write it. What, according to parallel axis theorem, according to parallel axis theorem, moment of inertia of any object about any axis is equal to the moment of inertia, so equal to the moment of inertia about moment of inertia, so equal to the moment of inertia about its parallel axis through center of mass, parallel axis through center of mass, COM, center of mass, plus the product of mass and the square of the perpendicular distance between the two parallel axes. Two parallel axes. Okay. So moment of inertia about parallel axis through its center of mass plus the product of mass of the body and the square of the perpendicular distance between the two parallel axes. I'll just give you the explanation of this particular statement. So let us suppose the moment of inertia of the given body is the mass of the given body is m, total mass is capital M, okay, and the moment of inertia about an axis, about an axis CD, which is actually passing through center of mass, okay, CD, I'm sorry, uh, moment of inertia, suppose this I is the moment of inertia about AB. So this is actually, okay, so moment of inertia, suppose, and see moment of inertia about the center of mass, I am writing C. This is the center of mass. CD is going passing through center of mass of the object, as you can see from the figure. Now, if I want to calculate the moment of inertia about this AB, so what it will be, according to the definition, moment of inertia of that this particular object, moment of inertia of this particular object about this AB, which is a parallel axis to this CD axis, which is passing through the center of mass, will be given by ICM plus m into, see, the distance between these two axes is m into, so m d square. So mass of the object into the square of the distance. So this is the statement of the theorem. So if you want to calculate moment of inertia of any object about any axis, okay, which is parallel to the axis passing through its center of mass, is given by. So moment of inertia about AB, so which is a parallel axis to this CD, which is passing through So see, AB and C. So this is actually parallel axis theorem. So you should be knowing what are those two axes. So this is AB and CD. So these are actually parallel to each other. And the center of mass will be always passing perpendicular to the plane of the object. Okay, plane of the object. All right. So this is center of mass. C like axis passing through the center of mass. I can write this is ICD also. CD means so similar to this ICM. ICD or ICM is the same thing. So better to write ICM only because this is the standard notation. So moment of inertia of any object about any axis which is parallel to the axis passing through the center of mass is given by the moment of inertia of the object about an axis passing through its center of mass plus the mass, the product of the mass and the square of the distance between these two parallel axes. Okay, so I'll just quickly prove this. Okay, I'll just like I'll remove. So theorem I'll write in terms of this ICD. Suppose I have to find the mass of this object is capital M. Suppose okay, so ICD it is given by ICM plus not ICD IAB, so which is the parallel axis m into d square. So this is the thing we have to prove. So to prove it, actually, let us take one mass, point mass. Okay, suppose this mass is actually obtained by summation of this mass. Okay, so I'm taking a point mass at x distance from the center of mass. Okay, so if I want to calculate the moment of inertia of this see particular object about this AB, so what I'll write? So I'll write m into x plus d whole square. This is the thing I'll write because this distance is, so see, this is the total distance of this particular object. Okay, so moment of inertia of this particular point mass about this AB axis will be given by m into distance square, so x plus d whole square. All right. So look here. If I want to calculate similarly the moment of inertia for the whole object, I'll just take the summation. That's all. Because I'm taking this point mass. Identically, I'll take another point mass, etc. Okay. So I'll take the sum of that. Then I'll get the moment of inertia like this and sum it over. Okay. So look here. If I just break this square term, whole square term, so what I get? So summation over this x square. I'm just writing. Look here. Mx into d. Okay. Okay, so 2 may be out of this and plus m into d square, this also summation. Okay, so look here what I'm saying. See, this is nothing but moment of inertia about the center of mass. Look, this much m into, so this is actually m x square. Okay, this is, and see, this will be total capital M into summation of xd. Let us write this, and this will be m capital D square. Okay, so this is nothing but the moment of inertia of this particular object, the whole object about center of mass. I can write this. So then I'll write this m d square, and this term is going to be zero here. Okay, this term is going to be zero. Why is it so? This is zero because a body can be balanced by its center of mass. An algebraic sum of the moments, because see, center of mass. So if you take another x distance this way, that way, anyway you take, so this will be actually identical. See, summation of mx, summation of m x, I'm sorry, this is um I have written little little bit wrong here. I'll write here D maybe going out. I can write this. So this is called mass moment. This is called mass moment. Mass moment. Since any object can balance about center of mass, that's why all algebraic sum of this mass moment will be always 0. So summation over mass moment about the center of mass will be always 0. So mass moment about center of mass will be 0. Okay, mass moment about center of mass is always 0. That's why this is going to be 0. So what we get if we just remove this part, so we can prove in this way. Okay. So we have proved the parallel axis theorem and perpendicular axis theorem. And next day, what we'll do, we'll we'll take the application part of these two theorems. Okay. So I'll stop it here for today. And next day, we'll actually take various examples which we can solve with these two theorem with the help of these two theorems. Okay. So bye for today. I'll stop it here.